Thank you to everyone for attending today. My name is Kevin Donahue, and I'll tell you a little bit about ceramic membrane technology and then how they're used at a plant that's operating in Australia at a lithium mine. So first things first, some of you may be familiar with membrane filtration already. This is just a display to show the kind of range of separation capabilities with membrane filtration. One thing I want to make note of is that ceramic membranes are used only in the range between nanofiltration and microfiltration. Today, there exists no reverse osmosis ceramic membranes. So that's kind of I would say, the new frontier for the technology. So, until today or until the foreseeable future, we're just talking about nanofiltration, ultrafiltration, and microfiltration membranes. Next slide, please. So ceramic membranes are generally made from inorganic materials. They can include silicon carbide, alumina, titania, zirconium oxide, and silica. Now, one thing that's interesting to note is that the membranes are made on a support. So the support can be either silicon carbide or alumina oxide, typically. But the membrane coatings are more diverse. You could have a coating that's composed of zirconia on a silicon carbide support or an aluminum oxide support. So there's a lot of flexibility in designing the actual membrane separation layer. And as I mentioned before, the ceramic membranes are used in the nanofiltration, ultrafiltration, and microfiltration ranges. Generally, today you can get a nanofiltration membrane with a rated cutoff of 250 Daltons. And then on the microfiltration side, you can go all the way up to about 1 micron or so. And one of the advantages of the ceramic membranes is they withstand strong acids, bases, and solvents. So you could think of the ceramic membranes as being chemically inert to almost any kind of process fluid. And because they're made out of inorganic materials, they're very robust, they're very strong. They offer very good tensile strength and resistance to abrasion. And one property of ceramic membranes that's very important in filtration applications is the fact that they're more hydrophilic compared to polymeric materials. Again, the next slide, we'll talk about hydrophilicity. Sorry. So today we're going to talk about tubular ultrafiltration membranes that operate inside out. Those are the products offered by Alsys. In the market, there are other types. There are flat sheet, there are hollow fibers, and so forth. But today we're going to talk only about tubular ceramic membranes. And what you should know is that as a manufacturer of the membranes, we have complete control over the scope of supply. So, we're buying powdered mineral products. We manufacture the porous support tubes. We coat the tubes with a membrane material, and we actually design and build the housings, and we can provide the skids and a complete plant to use the membranes in. We also have a kind of a flexible approach. Sorry, we could go back to that previous slide. We also have a flexible approach in that sometimes we sell membranes only to system integrators, and in other cases, we can provide the entire system to an end user. So it all really depends on how the end user does business. We can match up our sales channel to match the user's needs. Sorry, next slide now. So just a very simple and brief description about how ceramic membranes are made. So again, in this case, we're talking about tubular membranes that operate on the inside out. That means the feed is pumped in the inside of the tube. It travels from one end of the tube to the other. And then the permeate is exiting the circumference, so the outer wall of the tube. And what we're showing here is some cross-sectional views of an actual tubular membrane. And you can see the difference in appearance. For example, that image on the left, we're showing, and on the top of the image would be the feed channel. This is where the liquid is being pumped over the membrane surface. And then that area that's highlighted in the square, that's where the actual separation layer is created. And what we do to make these membranes, first we make the porous tube. The tube could be something like 20 or 30 or 40 microns of thickness. And then we coat the tube with different materials to create a tighter and tighter or more dense structure. And I mentioned the materials before, but to create, for example, an ultrafiltration membrane, we might first make a microfiltration membrane and then put an ultrafiltration membrane on top of that. So this is really the key technology and key capabilities that we have as a company, is the ability to, develop these coatings, these procedures, to manufacture them efficiently and cost effectively and reliably. It's quite a bit of technology involved here. Applying these films requires very precise control of the particle size, of the coating conditions. And then another point to mention here is that the coatings go into a kiln after each application. So some products might go into a kiln 3 or 4 times before the finished product is ready. So again, you must have very tight and strict quality control standards to produce these products. Next slide, please. So this is just a photograph to show you what a Ceramem brand membrane looks like. This is a cylindrical device. It's 34 inches long. It's 5.6 inches in diameter. And what we're showing you here is a device that has 2 millimeter square feed channels. So on each end of this device, there's about 1,500 individual tubes or feed channels in parallel with each other. And so I'll explain how this device works in a minute. But again, this membrane is available this particular membrane is available in anywhere from 5 nanometer up to 0.2 micron pore sizes. Next slide, please. This slide is showing the CleanStep brand tubular membranes. And it's the same, you could use Ceramem and CleanStep in some of the same applications, but this is an entirely different manufacturing technology. These membranes are made using aluminum oxide as the support material. And they also have different type of feed channel designs. With the CleanStep, we're using more of a circular or perhaps an oval shape. It gives us more variety and more flexibility with our feed channel designs. And here we have, right now, we have more flexibility with the molecular weight cutoff and the retention capabilities. These membranes can be supplied in cutoffs as low as 1,000 Dalton or up to 1 micron pore size. And these membranes also have FDA approval. All the components that we use to make the CleanStep membranes are approved for food contact. So they're being used in applications such as wine processing, beverage clarification, juice clarification, potable water filtration, any kind of application that might involve a product to be ingested by humans or animals. So whether it's a CleanStep or a Ceramem membrane, the principle of operation is the same. You have a channel, or it could be circular or square, which is showing a square channel here. But we're pumping the liquid, through the tube from one end to the other. And typically we run anywhere from, 10 PSI up to 40 or 50 PSI. And typically the solids have some kind of suspended matter in them. And what happens, the suspended matter accumulates, or I'm sorry, it doesn't accumulate, it contacts with the membrane surface. And we try to minimize the thickness of the solids on the membrane surface by using a high velocity. We like to operate under shear flow conditions or turbulent flow conditions so that we can minimize the gel layer, boundary layer conditions on the surface of the membrane. And then the permeate will travel through that gel layer and into the porous support tube or the porous monolith. And then from the monolith, it exits typically to atmosphere. So what's interesting is that, sorry, if we could go back to that slide, please. What's interesting to note here is that it's really the properties of that boundary layer that govern the rate of filtration more so than the membrane itself, you know. So that's really where we come in. That's where this choice of membrane can come into play. It's not just selecting a certain pore size. You must take into account the following characteristics of the fluid on the membrane surface. Okay, next slide, please. So this is just kind of finalizing a description about how the membranes operate. It's showing the feed going in one end. The retained material is coming out the other end. Now, I should say that typically, because we're running at a very high cross flow rate, it could be anywhere from 1 meter per second up to 5 meters per second. The liquid is not concentrated very much in a single pass. So typically, less than 10% concentration would occur in one device. But the permeate is exiting through the wall, through through the circumference, through the outer wall of this device, and is captured, for collection. Okay, next slide, please. So the key benefits of the ceramic membranes, as I mentioned before, they're robust. They can handle extreme concentrations of oil and grease or suspended solids. They can run at high temperatures. We have some customers using the membranes for purification of oil, and they're running at, like 200 or 300 degrees centigrade for that application. They can tolerate, basically any amount of acid or caustic, which is very useful when it comes to cleaning the membranes. And when you have if you have a tough cleaning application or a high fouling fluid, we can use very aggressive cleaning chemicals without affecting the life of the membrane. And the membranes are engineered to be abrasion resistant. In fact, we've developed a model. If you were to provide us with a particle size distribution and composition of particles, we can predict the life of the membrane based on the composition of those solids and any possible effect of abrasion on the membrane. And with ceramic membranes, you're going to achieve a very consistent and constant permeate quality. That means even if the feed composition changes or you have an upset condition, your permeate composition, your permeate quality will be unchanged because you have a permanent barrier against the contaminants. And because the membranes are so hydrophilic, they're so efficient, they produce at such a high rate, you have a very compact system design. It's typically, and if you look at a footprint for a ceramic membrane system compared to a polymeric system, it could be 3 to 5 times as compact or less. Could take up 3 to 5 times less space compared to the polymeric cross-flow unit. And all this combines into a low life cycle cost, because the membranes last so long. Usually the membrane life is not considered as part of the NPV determination. You don't have to budget into your costing any membrane replacement. So it makes for a very low life cycle cost.